Yeah, so I'm going to talk about today metastability of magnetohydrodynamic MHD atmospheres and their relaxation. So this is work that I've done with Dave Wasserman and Steve Kavli at Princeton Plasma Physics Lab. The motivation is explosive releases of energy in both astrophysical and magnetic confinement fusion plasmas. The deduction from the existence of such processes is that these plasmas exist in a higher order, in a higher energy metastable state. There's some relaxation down to a lower energy state, and a corresponding release of energy, a finite amount of energy comes out. Now, in these systems, it's typically believed that the stabilization, this little linear stabilization, is provided by magnetic field line bending, the field line bending force. But I'm going to talk about a simpler kind of metastability today. I'm going to talk about purely convective metastability. So what do I mean by that? I mean, when you take a parcel of fluid from one position, from one height, and move it to a new position and ask what's the force on that, I want to look for a system. I want to demonstrate that within MHD, I can have cases where if I move that parcel of fluid just a little way, the force will be restoring. But if I move it a long way, the force will be destabilizing. So that parcel of fluid will be sitting in a metastable state. Now, that's not possible in hydrodynamics. So let me just justify that. So I take a parcel of fluid. I'm going to assume some general equation of state. And I'm going to move my parcel of fluid from Z1 to a new height, Z2. The buoyancy force on it is just, its volume in its new position times the difference in the densities of the inside of the blob and the outside. This is the Archimedes force. Okay, and I can rewrite this as the force per unit mass on the fluid parcel in its new position is equal to basically this, the ratio of the inside and outside densities minus 1, and I'm going to write that as e to the r minus 1, where this number r is just the logarithm of the ratio of densities. So this turns out to be a convenient thing to do. But r is a proxy for the buoyancy force. So now I can write r as an integral between z1 and z2, just formally as an integral of d log rho by ds times ds by dz. So that's just a formal statement. I've got a difference S2 minus S1, so that's just a formal statement. And this fraction here, this derivative here is less than 0 in general. And I got a general equation of state, so it's less than 0 if I have a fluid where heating leads to expansion. So we assume that that's generally true, and then this thing looks like this. And when I take the linear limit, where I take z2 minus z1 goes to 0, that gives me the linear restoring force, which is stabilizing provided entropy increases upwards. Okay, so that's just the Schwarzschild criterion. So that's linear stability. But it's also nonlinear stability, because if I take this ds by dz is greater than 0 and stick it back into my original equation, I see my original expression for r, I see actually that ds by dz is greater than 0, means that this thing is always negative when S2 is larger than, when Z2 is larger than Z1, and so the force is always restoring no matter how large the displacement. So you cannot have metastability in hydrodynamics, but you can have metastability as soon as you introduce a new source of pressure. So now I promote my blobs to magnetic flux loops, and I let those, to magnetic flux tubes, and I let those be interplane, and I now have a new quantity which my density depends on. For example, the magnetic flux per unit mass, so that's what's conserved in MHD, but actually this is a general statement. If I just upgrade with a new source of pressure, I can always now have metastability. So my operation before, my formal integration to express this quantity r now looks like this. So I use the chain rule, I now have a ds by dz and a d chi by dz. That gives me the so-called modified Schwarzschild criterion as my expression for linear stability. And now I can no longer assume, I can no longer take this expression, stick it back in here and say, oh, well, actually, I always have nonlinear stability, because you see that this is a weighted sum of ds by dz and d chi by dz, just like this is, but actually the weights are now evaluated at a different pressure. So I can't stick that back in here. And so I can no longer conclude that I'm generally nonlinearly stable. And in fact, if one of my, so, I mean, it's clear that a necessary condition, but not necessarily sufficient to have nonlinear instability of this kind, is that one of my gradients has to be negative. For if they're both positive, then I'm back to this nonlinear stability. Okay, so I can get a little bit more insight into this by rewriting R in the following way. So this is another formal expression for R that just follows from considering how it changes as I go along from Z1 to Z2. If I just integrate dr by dz along that path, then I get this. And the advantage of this expression is that it separates now the integrated linear response, there's that L, which I know has to be positive if the thing is going to be stable, from the nonlinear response, which turns out to depend exactly on the difference in compressibility, the dimensionless compressibility between the tube that I move and the material that it moves through. So if the compressibility of the tube that I move, or the fluid that I move, is greater than the compressibility of the fluid that I move through, then it's possible that this nonlinear response term will be positive, will be destabilizing, and can overcome the integrated linear response if that thing is stabilizing me. I just want to point out that this effect is not contained within Boussinesq approximation. It's not within magneto-Boussinesq approximation. It relies on the nonlinear response. This is despite the fact that if L is very small, then the length scale on which metastability can be triggered may actually be arbitrarily small compared with all the other stratification scale heights. So I can be metastable over a really short distance if L is small. In the case of MHD, so now I actually specialize. This is only the first time that I specialize. I have S. I imagine S to be entropy. So, well, S was always entropy, but S, I'm going to assume this form. Any positive increasing function of entropy is fine. So I used P to the 1 over gamma. Gamma is the adiabatic index, divided by rho. Chi is the magnetic flux per unit mass. P is the total pressure, thermal plus magnetic. And beta is the ratio of the thermal pressure to the magnetic pressure. And so I then work out d log rho by d log total pressure. And that turns out to be this. And the point is that this is an increasing function of beta. So unmagnetized fluid, that's large beta fluid, is more compressible. And metastability occurs when less magnetic fluid moves through more magnetic fluid. So let me just kind of maybe bring this to life a little bit with a video. So here's the same atmosphere on the left and right. It's a metastable atmosphere. So I'm going to, and in both cases, I'm just going to apply a little Gaussian velocity perturbation. And on the left-hand side, that velocity perturbation is smallish. It's not large enough to overcome this linear stabilizing response of this fluid. On the other side, I just hit the thing just twice as hard, and I get a completely different reaction. This one has gone unstable. I've pushed my tube over the potential bump. Okay. So now I want to think about the relaxation of a metastable atmosphere, and I'm going to assume that I can clear this potential barrier, and the system is then allowed to shed its excess energy. So I'm not worried about energetic constraint. I'm going to assume that my system can get from this higher order state to this lower energy state. The excess energy is going to be propagated away somehow, and so we'd like to predict this state by minimizing the total energy. So can we do that? Well, so the energy is this. Pressure plus thermal energy plus magnetic energy plus gravitational potential energy. Now, an important step is to integrate this by parts and introduce m, the supported mass at height z. So this is the column density. This is the mass supported by the fluid that is at height z, and that's equal to the total pressure. That times G is equal to the total pressure by equilibrium. What that's done for me is it's created an expression that is just that's an integral of an energy function of m, s, and chi, s the entropy, chi the flux. And so what this does for me is it's now turned my relaxation. If I imagine discretizing my atmosphere into discrete slices of discrete mass, slices of equal mass, it's turned my relaxation into a problem of finding the optimal permutation of slices that minimizes the energy. Now this is non-trivial in MHD, because no restacking rule exists in the finite beta case. So what I mean by that, at large beta, I would just restack these slices by their entropy. I would have entropy increasing upwards, and that would be guaranteed to minimize the energy. At small beta, I would stack the slices by their flux, and that would guarantee to minimize the energy. But at finite beta, it's unclear how one balances those competing imperatives of maximizing entropy and of having entropy increase upwards and flux increase upwards. And so in principle, one might worry that one actually has to check n factorial permutations of these slices. But one doesn't have to do that, and it's thanks to this change of variables to the supported mass. Actually, this is not a problem of optimizing a permutation. This is a problem of optimizing an assignment. And what I mean by that is that there's a well-defined energy for assigning a slice to a particular supported mass that is independent of where I've assigned all the other slices. So it's simpler. I see 5 minutes left, right? Okay, so how do we solve this assignment problem? Well, it's the problem of assigning agents to tasks, where there's a cost associated with assigning an agent to a task. So here's an example. I've got some agents, I've got some tasks, and I've got some costs associated with assigning these agents. And all the agents have got to be assigned to tasks, and all the tasks have got to be assigned. There's an algorithm within combinatorics theory called the Hungarian algorithm that does this. It exploits the fact that if I shift the rows and columns by a constant amount, that just corresponds to a discount in the agent task assignment. And so there's a prescription where basically I subtract constant amounts from rows and columns, and eventually I end up in a situation where the optimal assignment is obvious because any change, any deviation from it necessarily incurs a positive cost. So that's how one goes about solving this problem. And Nick Fury is happy because he saved the world for minimum expense. This is the result of solving that minimum energy problem for the MHD atmosphere. So what I'm showing here is initial state of entropy against height, and then I've got the final state of entropy against height. And what you immediately see is that it's foliated. It's stacked alternating slices from different original positions next to each other and arbitrarily close to each other with the scale of foliation set by delta M. How to interpret that? Well, what's happened here is that I've assumed a 1D ground state, but actually the ground state isn't 1D, it's 2D. And so I pick out, I can determine the sort of proportion of different types of fluid at each height just by looking at the horizontal fraction, just by looking at the proportion of the slices, and so that's what I've done over here on the left. The horizontal scale is unconstrained energetically. It depends on the dynamics. It depends on the Reynolds number. If the Reynolds number is small, then I expect to have large-scale structures. And so this is a simulation showing me that, in fact, that's what happens. This is the real simulation. This is the same simulation with entropy sorted horizontally by height. And when I let that go, you'll see why I've done that. So this is large Reynolds number relaxation. And in fact, that 2D state is achieved. And these are two different simulations with slightly different initial conditions, just showing that, yes, you see a similar thing if you apply a different initial size, a different initial amplitude perturbation. Although as the amplitude of the initial perturbation goes down, the sort of degree of relaxation reduces, and so you don't get such a large 2D structure. You only have partial relaxation in that case. Okay, for lack of time, there's a second example. You can have metastability downwards. Same thing happens, and the same thing happens. You know, so the message of this is just that wasn't really a fluke. So there we go again. Right, in the very short amount of time that I have left, I just want to tell you about how we're thinking about relaxation at large Reynolds number. So this is when the Reynolds number is large. Your 2D structure then is not large scale, it's arbitrarily small scale. It's set by viscosity. It's set by the Kolmogorov scale. So let's just see what happens when we do this at large Reynolds number. There's turbulence, there's mixing. Same thing for the downwards profile. Can I still play restacking games to get some idea of what's happened in these two relaxations? So this is how we're going to think about it. In a closed system, the energy liberated is transferred to the velocity field. It becomes turbulence. S and chi, my invariants, my advected invariants, are going to be mixed chaotically. They're going to develop stochastic structure. Eventually, they're going to reach diffusion scales. But I'm going to assume that I can think about this as a timescale separated process. I'm going to imagine that there's a separation between the dynamical timescale and the dissipative timescale, and that the slices become well mixed while preserving their S and chi before diffusion happens. So this is analogous to the theory of sort of collisionless relaxation or violent relaxation developed in the context of stellar plasma stellar plasma and vortex kinetics by Lyndon Bell and others. So this is how that theory works in a nutshell. I'm going to have a stochastic distribution of S and chi in my final state, and so I should describe them probabilistically. So I introduce the probability density function to find the fluid at supported mass m to have a particular value for S and chi. So that's the probability density function. I'm assuming that I have the most mixed possible configuration of those slices subject to the conservation, subject to the relevant constraints. And so what I do is I maximize the mixing entropy subject to those constraints. So this is the mixing entropy, P log P, and I maximize it subject to normalization of probability, conservation of energy, and fixed mass of fluid with each value of S and chi. That's equivalent to maximizing something with Lagrange multipliers representing those constraints unconditionally, and I derive a solution for that probability density function. The relaxed profiles of S and chi, well, naively, I compute these by taking expectation values of this probability density function. But there is a problem. This is not going to conserve the energy. And it also has conserved entropy, not thermodynamic entropy, but real entropy, which actually should increase. And so to solve that problem, I can't really talk about it very much. I actually determine the predicted entropy by imposing energy conservation at each height. So I impose that mixing in the relaxed state, in the state that's maximized the thermodynamic entropy, is going to be local. It's going to happen locally at each height once the relaxation has happened. That gives me a prediction. So here's the statistical mechanical prediction overlaid on top of the restacking solution that was the minimum energy state, and in blue, purple, and red, you're going to see the results of the numerical simulation. And the blue one is the one with the highest energy. These guys are energies that I only saw a partial relaxation for before. So once I've started to see good sort of mixing, but not complete diffusion, so that's just a particular time in the simulation, I actually find very, I think, reasonable agreement between this at this energy that I saw good relaxation in the small Reynolds number case, fairly good agreement between that prediction and what the simulation does. But later times where everything is sort of mixed to basically has become much more diffused, has become much more constant in X, I find again reasonably good agreement. The same thing for the downwards profile. So I've got this downwards profile. This is the non-linearly relaxed state. This is the highest energy relaxation, the highest energy simulation, and it agrees really quite well with the prediction of that statistical mechanics. So there I am. So this is my summary. Unlike in hydrodynamics, a stably stratified atmosphere with two sources of pressure is metastable, sufficiently close to marginal linear stability. We've determined the minimum energy states which are consistent with those fluid element-wise conservation laws by solving a linear sum assignment problem, a combinatorics problem. And we find that the ground state is typically two-dimensional. These two-dimensional ground states reasonably well reproduced by simulations at small Reynolds number, although if the initial velocity is not large enough, then there's only a partial relaxation. And at large Reynolds number, we model a relaxation with a statistical mechanical treatment. It's based on Lynden-Bell's theory of violent relaxation in stellar systems, but we've applied it to this problem. And again, the predictions of that theory are reasonably well produced in our numerical simulations. So thank you very much for your attention.
Hi, I'd like to give you a hydrodynamic example of this metastability.
Yeah.
It's moist convection in the atmosphere, because if you lift a moist parcel of air high enough,
yeah,
the water will condense,
yeah,
and that'll be the equivalent of your variable compressibility.
right.
And then they speak of conditional stability, conditional on the vertical displacement not exceeding a value so that you cross the so-called lifting condensation level.
Okay.
And another analogy concerns your vertical restacking.
Yeah.
There's something called the Thorpe scale. There's a minimum energy state of the total potential energy along a vertical sounding that's obtained. You look for the restacking that gives you the minimum, basically a minimum energy state of the system.
Yep.
And the mean absolute displacement that you have to do in order to achieve that is called the Thorpe scale.
Okay, thank you. I'd love to talk to you about that a little bit more. Afterwards. No, I'd love to talk to you about that. I just point out that the hydrodynamics example isn't in contradiction with my, because my is a very restricted definition of hydrodynamics. It's where you have an equation of state, a density that depends only on total pressure and on entropy. But you're talking about kind of a two-phase system there. So that's so that you're much closer to sort of the MHD thing. Yeah, right. Yeah, sure.
But it's so analogous to what you're talking about.
Right. Thanks very much for your comment.
Yeah, I think your 2D MHD picture is very unphysical, because you don't have flux tubes that are horizontal sitting above the atmosphere. What you have instead is loops that go from one point on the sun and go up in the sky and they go down again. And if they go up, then they get stretched in the axial direction, and that takes a lot of energy, and that will prevent them from going up. So this whole idea of them rising up like a balloon isn't going to happen.
Well, okay, so I guess two things. So I've picked this model, this sort of simplified system, not because I expect it to be a very good model of the actual physical phenomenon. I pick it because you can do a lot with it.
But it's not related. But you shouldn't call it. I mean, you're giving people the impression that it's describing a real system, but it can't.
Well, so in the real case, when you have these flux loops that stick out of the solar corona, you have some destabilization from the buoyancy force, but you have stabilization from magnetic field line bending. The nonlinear theory, the weakly nonlinear theory, is fairly well developed in that case, and you have eruptions, you have explosive eruptions.
Yeah, but that's not hydrodynamic effects. That's from magnetic effects.
Yeah,
that's from magnetic fields blowing it up. It's not because of hydrodynamic effects or buoyancy.
No, that's right. But the issue is, in that case, it's very hard to treat that problem. That problem is very difficult to simulate. It's very difficult to answer questions like, what's the ground state? How much energy are you going to get out from a relaxation? Is relaxation going to be complete? And all of those questions are answerable within this model.
Could you comment on the prospects for experimental or observational confirmation of these ideas?
Well, it sounds like they potentially may not come from magnetohydrodynamics. I think that would probably be the, well, okay, so taking into account the objection just raised, one can design an experiment where one sees explosive releases of energy in a magnetized system. That's a tokamak, for instance, with a disruption event. Now, I understand the physics is slightly different, but that's a like example. And it sounds like directly analogous metastability is observed and can be tested in atmospheric science.
When the thunderstorm just out of the blue,
Right.
an example where there's been a perturbation big enough to break the metastability of the clear air.
Right. Thanks.
Okay, let's thank David again.